Hello students, in this video you will find amorphous solid and type of crystalline solid. Then first, amorphous solid. Amorphous solid. What is amorphous solid? A solid substance in which the constituent particles are arranged randomly or which have irregular arrangement of particle and hence doesn't have definite or regular characteristic shape is called amorphous solid. Now, properties of amorphous solid. First, nature. These are pseudo-solids. Pseudo-solid. Second one, isotropic property. These are isotropic. Some of the physical properties like electrical resistance, electrical conductivity, refractive index, etc. that is same when measured along different direction in the same solid. Next, cleavage planes. They do not have well-defined cleavage planes like crystalline solids. That is, when cut with a sharp-edged knife or tools, it gets fractured. Means the pieces obtained do not have plain and smooth surfaces. The new surfaces generated, the new pieces obtained, they have irregular surfaces. Remember this thing. Number 4, heat of fusion. Amorphous solids do not have a definite and characteristic heat of fusion. Melting point. Amorphous solids do not have sharp melting point. When they are heated, then over a range of temperature, they begin to flow, but do not melt abruptly at a definite temperature. Hence, they do not have sharp melting point. Number 6, symmetry. They do not have crystal symmetry like in crystalline solids. They do not have crystal symmetry. When rotated about a axis, then their appearance changes. Next, some example I am telling, like there is coal, charcoal, rubber, plastic, wax. These are amorphous solid. And some uses also I am telling you. Amorphous silicon is used for making photovoltaic material, which is used for converting light energy to electrical energy. Now let us see next last point, arrangement of constituent particles. Constituent particles are arranged irregularly or randomly. Now next point is type of crystalline solid. Type of crystalline solid. Now our crystals. First, molecular solid. Molecular solid. Molecular crystalline solid. In these solids, the constituent particles are molecules. First point. And second point, the force of attraction holding these molecules together in the crystal lattice of this type of solid is van der Waals force of attraction. Van der Waals force of attraction is weaker than the valence bond forces. Some example of molecular crystalline solid like solid SO2, solid CO2, etc. Now let us see ionic solid. Ionic solids. Ionic crystalline solid. Ionic crystalline solid. In these solids, the constituent particles are oppositely charged ions. Positive ion means cation and negative ions. Second point, these oppositely charged ions are held together, attracted towards each other by strong electrostatic force, Coulombic force of attraction. Third point, ionic crystalline solids means ionic compounds, they do not exist as individual discrete molecules. They exist as the aggregate of oppositely charged ions arranged in 3 dimensions in the crystal lattice. And one example I am going to tell you, structure of sodium chloride. Structure of sodium chloride. Structure of rock salt, sodium chloride. First, I am making one unit here, sodium chloride. Here like that, Na plus Cl minus, Na plus Cl minus, Na plus Cl minus, Cl minus, Na plus, like that particles are arranged, 4 Na plus 4 Cl minus. I am going to tell you now first point. In NaCl rock salt structure, sodium chloride structure, Cl minus radius is around 181 picometer, bigger than Na plus. It adopts CCP, cubic closed piping arrangement, or FCC arrangement, in which, second point, Cl minus occupies the corners of the cube, and also it occupies the center of each face in the cube. Cl minus occupy corners as well as the center of each face. It adopts FCC arrangement. Third point, Na plus in NaCl structure occupies the octahedral void. It is present at edge center and at the body center. 12 edges are there, then on each 12 edges are there, on the center of each edge Na plus is present, and in the body center of the cube also Na plus is present. Next point, fourth, each Cl minus at the corner or wherever it is, each Cl minus is surrounded by 6 octahedral void, and in each octahedral void Na plus is there. So each Cl minus is surrounded by 6 Na plus, and each Na plus is surrounded by 6 Cl minus. Now next point, as I told you, there is one octahedral void per atom. Hence, for each Cl minus only one Na plus is there. Number of Na plus and Cl minus is equal. Then radius ratio in NaCl, radius of cation by radius of anion. Na plus radius around 95 picometer and chloride radius around 181 picometer. It comes around 0.524 or 525 you can write. And this ratio represent the octahedral arrangement of Na plus and Cl, octahedral arrangement of ions, and coordination number of NaCl is 6:6. Coordination number of sodium ion and chloride ion is 6:6. Now next point is number of chloride ion per unit cell equal to, they occupy the corners, 8 at the corners, into 1/8 plus 6 at face center, 6 at face center into 1/2. Then it is coming 1 plus 3 equal to 4. there are 4 chloride ions per unit cell. Now number of Na plus ion per unit cell, there are 12 present at edge center. Edge center, at edge center, and again each edge particle is shared by 4 neighboring unit cell plus 1 at the body center of the cube. 1 at the body center of the cube, then plus 1 here written already at the body center, then it is here 3 plus 1 equal to 4. There are 4 Na plus ions in the unit cell. Thus, the stoichiometric ratio of Na plus and Cl minus is 1:1. Formula of sodium chloride is NaCl. Next and last point, the force of attraction between Na plus and Cl minus is Coulombic force of attraction, electrostatic force of attraction. That's all for today. Again, in the next video, you will find most important in very brief form next topic of this chapter. Thank you.